is 35 millimeters from the top, or right, or 100 minus 35, 65 millimeters from the bottom. Okay, then we are going to find our I1. Okay, so it's 160 20 cube over 12 plus by 3200 multiplied by 35 minus by 10 squared. Okay, so 160 times 20 power 3 divided by 12. So this is equal to 106.667. So write this number down when you calculate, okay? And then plus 35 minus 10 squared times by 3200 is equal to 2 times 10 to the power 6. So this is equal to 106.667 power 3 plus 2 power 6 is equal to 212.107 times 10 to the power 6 millimeters to the power 4. Let me do it again. 160 times 20 power 3 divided by 12 plus 3500 times by 35 minus 10 squared is equal to wait 160 times 20 power 3 divided by 12 plus by 3200 times by 35 minus 10 squared. Okay, so 35 minus 10 squared. I got a bit of different number, that's why I'm checking it again. Okay, it's correct. Okay. Then you have I2 is equal to I3. All right, so this is 2080 cubed over 12 plus by 1600 35 minus by 60 squared. Okay. 20 times by 80 power 3 divided by 12 is 853 times 10 to the power 3 plus, well, let me do it, 20 times by 80 power 3 divided by 12. Yep, so 35 minus 60 squared times by 1600 is equal to 1 times 10 to the power 6. So this is 853.333 3 power 3 plus 1 power 6 is equal to 1.853 times 10 to the power 6 millimeters for. Okay, so let me do it again. Power 3 divided by 12 plus 160 times by 35 minus 60 close bracket squared. Yep. Okay, so finally we can come up with our I total. So it's equal to 2.107 plus by twice because of I1, I2 and I3, which is the same, 10 to the power 6. So this will be equal to 2.107 power 6 plus 2 times 1.853 power 6 is equal to 5.813, right, times 10 to the power 6 millimeters for. I always want to work to the power 6, to power 3, 6, 9, and 12. So if now I convert to meters, I just need to do all 5. I don't need to press my calculator anymore, okay? So some of you leave to 10 to the power 4, 10 to the power 5. You're going to mess things around, okay? That's not a good practice in engineering, okay? So leave it in 3, 6, 9, 12. You get those increments, okay? Right. So now where we are now we know I, okay? So the next thing is we want to find QZ and T, okay? So we want to find position number 1, okay? So let me, any questions so far, anyone? Well, okay? Okay, so I'm going to copy this. Hey, come on, Eugene. Copy. Paste. Okay, and then I'll also do the same for the rules. Okay, I'm going to copy. So we know our centroid. Okay. Right. So we want to find the shearing stress or shear stress at point A. Okay. So we know we have Vy coming down. And Vy we found as equal 90 times 10 to the power 3. Okay. What I'm going to do next is to sketch the shear flow. Okay, I'm going to sketch the shear flow. And shear flow is like similar to what? Fluid flow. Okay. So your Vy start from the top. This is how your Q will look like. Okay. So this is your Q. And in fact, this will come over here. Okay. Right. It goes to the center, then it comes out. So now we already know, right? Okay, some of you are a bit confused how to. Okay, the way to construct the shear flow is this. Okay, the web. Okay, the web controls the flow. So you might ask me, Eugene, what is the web? Okay, so in any structure, this is known as the flange. Right, this is known as the web. It's such a pity only 3 of you show up out of 10. Okay, this is important stuff. But anyway, so usually it goes from the top to the bottom. Right, so you construct here first. Right, so like fluid flow, if the fluid has to go into the web, right, it has to do this, right? It has to come here, and then the other side will have to come here, right? So this is how the fluid will flow. Okay. Now, this is just to train you how to design this. So these are all your small Q. Okay, these are all your shear flow. Okay, so this is how the shearing stress will flow. Okay, so now we're going to find the shear stress at point A, right? We're going to find the shear stress at point A. So if you look at point A, right? So this is where I'm going to highlight. This is exactly point A is, right? So the first thing we ask ourselves is simply what is the thickness? Okay, so thickness, right, is equal to twice, right, 20 times 10 to the power minus 3. Okay, so the thickness will be equal to 40 times 10 to the power minus 3 meters. Why the 2 is here, one for the left, and the other one is at the what? At the right web, right? So you have one web over here, you have one. So the shear flow is distributed. Then the next thing you ask me, Eugene, why not 160 times 10 to the power minus 3 meters for thickness? Right? Right? If you look at point A, it's at the if you look at point A is at the intersection of the flange and the web. Okay? And why not 160 is because we want, because not we is because formulate the higher stress is more critical, right? So why I pick the smaller one? If we look at the formula, which is shear xy is equal to by over izz, right? Qz divided by t, right? If you pick 160, your shearing stress will be what? Lower. We want to pick the what? A higher value. It's just for this reason. Okay. Now, the more difficult part is what is the first moment of area. Okay. So we already sort out the thickness. So the first moment of area, so we know that our centroid, right? Our centroid is here. Okay, this is our centroid, roughly. Right, this is the location of the centroid. Oh, come on, Eugene. Right, this is the location of the centroid. So the area that we have to carry out is this area over here. Okay, it is this area that I've shaded, and it is not this area, not this area. Okay, it is not this area, but the top layer or the web. So why is this? Okay, why is this? Right? Why is this? Because of the way we derive the equation on Tuesday, right? We say what? Analysis starts from where? Y max. So this is the analysis direction. It is coming towards the what? Towards the centroid, right? It's not from the centroid, it go outwards. The analysis start from the centroid, start furthest away from the centroid at Y max, and then it comes in. This is the only reason. Okay. So as I say, the first moment of area QZ is the most difficult quantity to acquire if you don't apply these rules. Okay. So the area and then Y bar, right? Because the first moment of area is about the ZZ axis over here and it's from the centroid, right? Because the centroid is also known as the what? Datum, right? Okay, so the area. So the width, so area, as I said, my standard practice is I like to do width, depth, and Y bar. Okay, so width is 160, depth is 20, Y bar is equal to the centroid is at what? We calculated the centroid. Let me recall. I think the centroid is at 35. Okay, so 35 minus by 20 divided by 2. So what is this dimension that we're calculating? Is this dimension that we're calculating. So this is our Y bar. Okay, so it's equal to 35 minus 10 times 20 times 160 is equal to 80 times 10 to the power 3, and this is a millimeter cube. Let me do it again. 160 times 20 times by 35 minus 10 is equal to 80 times. Or, all right, watch this. I don't need to press my calculator. I just know that this is 80 times 10 to the power minus 6 meter cube. Done. No need to get the calculator info. Okay. So now all these are known, right? So we want to find the shear XY at point A now, right? So V is equal to 90 times 10 to the power 3, right? QZ is 80 times 10 to the power minus 6 divided by IZZ, IZZ, I can't remember. 5.813 times 10 to the power minus 6. And then the thickness is, we calculated the thickness is equal to 40 times 10 to the power minus 3, right? It is, the formula is easy, isn't it? Right? 80 power minus 6 divided by 5.813 power minus 6 divided by 40 power minus 3 is equal to 30.965. Right, times 10 to the power 6 Pascal. Okay, let me do it again. 90 power 3 times by 80 power minus 60 by 5.813 power minus 60 by 40 power minus 3 is equal to 30.9. And I have not a clue, or I don't know yet. I know, I think this answer is correct. Okay, I've not got the solution of the answer. Hold on, I can, oh no, it's okay. Okay, right. If there's anything wrong, I will tell you guys. Okay. Right. So this is point A is straight